it's like, it's kind of easy to see this because 2 is relatively prime to 3, so being odd doesn't really affect whether you're divisible by 3 or not. So it's still going to be about 1/3 of the integers are going to be divisible by 3, but 15 is divisible by 3, so you have like 5 that are and 10 that aren't. I guess you could write it out if you want to make it clear. Like it goes 1, 3, 5, 7, 9, 11. See, like every 3 is going to be divisible by 3. Yeah, and then you can basically see the same thing for 5. Like every 5 thing, or like 1/5 of the integers that aren't divisible by 2 or 3 will be divisible by 5. So out of these 10 that aren't, you get 2 that are divisible by 5. So the totient of 30 is 8. And I mean, in general, you can do a similar thing to calculate the totient of any integer. So I wrote like basically how you do it in theorem 1.3. If you have any integer n, you want to split it into like pi to the ei, here, the product, and then the totient of n will just be like n times and then p1 minus 1 over p1 and then so on, right? Because you just go through each of the primes and you're like p1 minus 1 over p1. This is like the number of, and like the ratio of things that are divisible by p to the ratio of things that aren't. And this will always work. If you want to like, if you want an actual proof to this, one way is to use Chinese remainder theorem, which I guess I might talk about later because today's gonna be about mod. So yeah. So now I guess we'll move on to section 2, which is about exponents. So Euler's totient theorem, I mean, it involves the totient function, but the totient function doesn't really help you much in a lot of like ways. So yeah, we need to talk about exponents because that's like the other thing that Euler's totient theorem is related to. So, so first we need to talk about modular arithmetic because yeah, hopefully everyone knows how mods work. If you don't, basically A equals B, you use 3 equal signs, means equivalent to. A is equivalent to B mod n, or I guess I said mod P, but it's really like mod n because it doesn't have to be prime. If like A equals like n times some integer plus B, or alternatively, they have the same remainder when divided by P. So yeah, or by n, well, whatever. So theorem 2.1 basically says that addition, subtraction, and multiplication are like, you can do these 3 operations, mod n, it'll work, but you can't divide. That's like the one thing you can't really do. You can usually divide when they're relatively prime, but but you have to be really careful. So now let's talk about taking exponents mod n. So a lot of times you'll want to like find k to the e mod n for some k, e, and n, right? So there's a lot of techniques you can use for this. I guess I'll start by talking about the Chinese remainder theorem, even though I left that out of the handout, because I think it's important to know. Usually, if k and n are not relatively prime, you want to like cancel out a factor of k and n, so that, and then you use Chinese remainder theorem afterwards to like put it together, basically, because you can really only deal with this expression when k and n are relatively prime. So yeah, now let's go through like a few variations of this. So in example 2.2, we want to use the binomial theorem to like simplify it because yeah. So we want 9 to the 2020. We want the last 3 digits of this. but that's just mod like 1000, right? And 1000 is 10 cubed. So anything with a 10 cubed, like if you have like 10 cubed times something, this will always be equivalent to 0 mod 1000. So basically, that won't affect the last 3 digits. So we can write this as 10 minus 1 to the 2020. And you'll notice that if you expand this out, like the first 2017 or whatever terms will all have a 10 cubed in them. So it just, like, you don't care about those terms, so you only care about the last 3 terms. So if we look at the last 3 terms, you get like 10 squared times 2020 choose 2. And then minus 10 times 2020, and then plus 1, right? And then you know that this term's obviously divisible by 10 cubed because you have 10 squared here. This should be divisible by 10. So you really only care about the last 2 terms, and that gives you like 200, negative 200 plus 1, which is like negative 199, which is like 801. Right. Okay. So yeah, this basically the main idea here is, since 9 also, this is generally useful when you get a 1 here, like in the binomial expansion, because then the 1 to the 2020 kind of like just doesn't matter. So if you see like 9 to the something, the last something digits of 9 to the something, then you do this, or like 11 to the something. Yeah. Okay. So sometimes you're not so lucky that you can just use the binomial theorem like that, and you get like ugly stuff. So the second case I have here is really bashy, but sometimes you can actually just bash it out if the exponent is small. So here we want 9 to the 10 mod 2020. So here 10 is like sort of manageable. I mean, you don't want to actually take 9 to the 10th power, but it's like still considered small, right? So instead of taking 9 to the 10th power, we want to take mods like in between, because mods are like, you can multiply and it's kind of still, everything still works basically. So yeah, I guess here, so for me, I see 10 as like 5, or 5 times 2. So if we can calculate like 9 to the 5th, all we have to do is square it. But 9 to the 5th is like, 5 is like 4 plus 1, which is like a power of 2 plus 1. So like you can just square to get 4 and then multiply by 9. So 9 is 9. 9 squared is 81. And then you can square 81. This is like, it isn't that much work to do. Right? And then you notice that these cancel mod 2020, so you get 501 is 9 to the 4th. Should probably write that. And then multiplying this by 9, you get 4509, which is 469. So all you have to do is square 469, which is kind of hard, but it's like one operation, so it's pretty manageable. So you get like 1801 after you do that out. Yeah, in general, especially when the thing you're trying to take mod is large, it's kind of like none of the other tricks really work for that. So sometimes you just have to bash it. Okay, and then lastly, I want to introduce the idea for when the exponent is large and the thing where like, and the n is small, and it's also, we can't just like do the first trick. The first trick you always want to try to use, but a lot of times you can't use it. So here, here I define the order, which is very important later. It's not very important right now, but the order, you'll want to know this, is the order of k mod n, this is I guess how we'd say it, is the, well, first of all, you need GC dk n equal 1, I guess, or else you can't really define it. And then it's just the smallest e such that k to the e is equivalent to 1. So yeah, I guess I'll go through the next example, which we can kind of use orders, but not really, I don't know. I mean, it doesn't really matter. Yeah, so in general, if you can find the order, or if you can find a multiple of the order, so any number such that like k to the e equals 1 mod n is like really good for these types of problems, because then you can basically take the exponent mod e, because you have k to the like ae is also going to be 1 mod n, because k to the e to the a is also 1, right? So this is true. So if you want k to the b, you can just like b minus ae, right? So you can basically just take b mod e and make it work. So in this problem, we want 2 to the 2020 when divided by 17, right? So here, we can just write out powers of 2 until we find one that's 1. So you get 2, 4, 6, 8, 16. You notice that 16 is negative 1, which helps because then you know that like eventually you'll get, or you can just write these as negatives, and you know that like this one will be negative 16, which is 1, because like negative 1 squared is 1. So we know 2 to the 4 is negative 1, which means that 2 to the 8 will be 1. So 8 is the order of 2 mod 17. And you'll notice that none of the residues before 1 are, like before 2 to the 8 are 1. So 2 to the 8's the order, like 8's the order. So now that we found a number such that 2 to the 8, like e is 1, we can just take 2020 mod 8. So we'll get like 4, right? Yeah. So we'll get just 2 to the 4, and that's just 16, which is negative 1. Or why? I don't, why? No, no negative 1. Please don't write negative 1 as your residue. I did that once. It was sad. Yeah. And you'll notice that we can't really work with 2020. Like, we can't bash it out the way we did when it was 9 to the 10. And you also can't really write 2 as like 17 minus 15, because then you'll end up with a 15 to the 2020, which is probably worse. So yeah. Okay. Well, sometimes bashing out small cases like we did here to find that 2 to the 8 equals 1 isn't really feasible, especially when numbers get bigger. So we need a theorem for this. And this is Euler's Totient Theorem. So it's a pretty simple theorem, actually. If you have an integer n, and you have k relatively prime to n, then you get k to the totient of n will always be equivalent to 1 modulo n. So this is a very useful theorem, especially when you're dealing with like k to the e mod n cases like we did before, because then you can basically always take your exponent mod the totient. But you need to be very careful about the relatively prime clause, obviously, but yeah. A lot of times when you see like something mod something, you really want to think of that, of this. So just a reminder about totient, it's basically the number of, or if people weren't here, I guess, it's the number of integers less than n that are relatively prime to n. So I'm going to go through a proof for the Totient Theorem. I actually found this pretty, I don't know, I looked it up earlier, and this proof is a lot simpler than I thought it was going to be. So yeah, it's pretty cool. Yeah. So if we just consider the set of everything that's relatively prime to n, so I shouldn't be using brackets, but so if you have like a1, a2, dot, 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 like a, obviously there's totient n things less than n that are relatively prime to n. So you'll have totient n numbers here. And we're going to multiply them all by k. So you get like ka1, ka2. Actually, I'm going to go through a concrete example to make this maybe more clear. So if you have like n equals like, I don't know, 8 or something, then this set will be like 1, 3, 5, 7 because 8 is divided by 2, so every odd number is going to be relatively prime to 8. So totient of 8 is 4. You have 4 integers here. And let's say we want k to be like 3. So you multiply everything here by 3. Then you'll have 3, 1, 7, 5. You do a mod 8, right? And we notice that this like set happens to be exactly the same as this set. So I claim that this will always be true, no matter what you choose for n and k. And to see this, first, I want to say that kai is always relatively prime to n. So like, right. Basically, to see this, you know that k is relatively prime to n, you know that ai is relatively prime to n, so kai must also be relatively prime to n. Yeah. So yeah. And then you want that like kai is not equal to kaj, or not equivalent to kaj for any I and j, right? And then if you have both of these, then you basically the second list also has to be all of the numbers less than n that are relatively prime to n, so it'll be the same as the first one, right? So kai is not kij, or kai is not kaj for any I and j. And to see this, I mean, we can kind of divide by k, but I said that division doesn't work, so we need to be more careful about this. So this is equivalent, like this would be equivalent to like kai minus kj equals 0, right? If this, like if these two are equivalent, then this would be 0. So then you can factor out the k, right? And then if this is 0 mod n, that means this must be divisible by n, right? So this would be like, yeah, this must be divisible by n. And since k is relatively prime to n, you need ai minus aj to be divisible by n for this whole thing to be divisible by n. And ai minus aj obviously can't be divisible by n because ai and aj are both smaller than n, I guess. Yeah, and they're different. So yeah, I mean, yeah, that's basically the proof of that. And then you go back here, and once you know that these two lists are the same, you can basically just multiply everything in the lists. So here you get a1, a2, a3, dot, 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 an. Here you get like the same thing, but you have a k to the totient of n. So that means that k to the totient n must be 1. Yeah. Oh wait, yeah, we can't do division, but you can if they're relatively prime. But I guess I should do it more rigorously. You have product of ai is equal to product of ai times k to the totient n. So this means that k to the totient n minus 1 product ai must be equivalent to 0. But since this is relatively prime to n, this must be divisible by n, so k to the totient n equals 1 mod n. Okay. Also, note that when n is prime, you get totient of n, or I guess I'll write totient of p for p prime. You get totient of p equals p minus 1. So then you get k to the p minus 1 is equivalent to 1. Or if you multiply both sides by k, you get k to the p is equivalent to k. I should write all these mod p's. And the nice thing about this is now we can get rid of the relatively prime, right? Because even if k is divisible by p, or if k is 0 mod p, like that's the only case where it wouldn't be relatively prime, you still get like 0 to the p equals 0, right? So so we have Fermat's little theorem, which says that for any prime p integer k, k to the p is equivalent to k, which can be nice because then you don't have to worry about the relatively prime clause. But in general, Euler's theorem is like a generalization. So yeah. Now let's go through some Totient Theorem examples. The first one is pretty simple. You want 2 to the 2020. You want the remainder ones divisible by 19, which basically just says you want this mod 19. So by Euler's Totient Theorem or Fermat's little theorem, whichever one you like, you get like 2 to the 18. So it'll be equivalent to 1, 18. So now we want 2020 mod 18 kind of, which is much easier than this, obviously. So like 2020 is equivalent to 6 mod 18. Alternatively, you can find something such that like 2 to the 18 times that will be like 2 to the 2014. So yeah, 2 to the 2026 mod 18. So then, wait, is it 6? I feel like it's not 6. Wait. I think it's 4. Cool. Okay. I don't know how to write handouts. I think it should be 4 because 2016 is by 9. 2020 is 4. So then you want 2 to the 4 mod 19, which would be 16. Right? Yeah. Okay. So basically the idea here is you find the totient and you just take the like exponent mod the totient, and then you get something that's really easy to calculate. So let's move on to our final example, which is you want the last 3 digits of this like really weird power tower thing, which is kind of like, it's 2008, not 2018. Okay. So you have like this thing and it goes all the way to 1, right? And you want to find the last 3 digits. Basically, whenever a problem asks you to find the last some amount of digits, it's just you want this mod 1000. It's just like mod 10 to something. And if something asks you to find the last so-and-so digits in a certain base, then you basically want your expression mod that base to the however many, whatever power you need. Okay, so mod 1000. I guess when you look at the problem, the first thing you notice is this is just 8 mod 1000, so you don't actually care. Like, it doesn't need to be 2008. Yeah, and then after that, you notice that this is obviously going to be divisible by 8. So we can like split this 1000 into 8 times 125. So obviously mod 8, this is going to be 0. So now we need to find this mod 125, right? Well, we know that 8 and 125 are relatively prime, so now we can use Totient Theorem of 125. So to calculate the totient of 125, you do 125. Since it's only divisible by 5, you only need to multiply by 4/5, so you get 100. So yeah, so totient of 125 is 100. So now we only care about the numerator mod 100, right? So we want, like, well, 2007 mod 107, so we can just write the 7. And then to the 206, dot, 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 1, mod 100. Yeah. So now 7 and 100 are still relatively prime, so we can do the Totient Theorem again. And the totient of 100, now it's divisible by 2 as well, so you have to multiply by 1/2 and then 4/5, so you get 40, right? So now you only care about the numerator thing, which is like 2006, or 2005, dot, 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 mod 40. And I think it's pretty obvious that this thing's divisible by 8, because 2006 is even, and this is way more than 3. So we can just say this is 0 mod 8, and we want to calculate mod 5. Well, mod 5, 2006 is obviously 1, or because 2005 is divided by 5, and 1 to the anything, mod anything, is just 1. So this is just 1 mod 5, right? So now it'd be tempting to just plug the 1 back in here, but we obviously need to remember that's also 0 mod 8, so we need to find this expression mod 40. Chinese remainder theorem has like an actual theorem where you can calculate, like given this and this, you can calculate a mod 40, but I tend to just like trying things. So 8's not 1 mod 5, but if you multiply by 2, 16 is 1 mod 5, so that's your residue mod 40. So we figured that this is 16. So now we need to plug 16 back into this top expression, because we've determined that, yeah, we've determined that 7 to the 2006 to the dot, 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 this is just 7 to the 16, right? And with 7 to the 16, you can use, since 1 is 16 is a power of 2, and it's relatively small, so it's really easy to compute things to the power of 16, mod things. So you get 7 is 7, 7 squared would be 49, 7 to the 4th is like, I think it's this, right? So it's equivalent to 1. Am I? Is it 2501 or 2401? I don't know. It's 2401. I can't do math. But yeah. Okay. This is 1, which is really nice because 1 to the 4 is still going to be 1. So we know this is just 1, right? So now we can go back to the expression all the way back here. So we want 8 to the 1 mod 125, which is just 8. So now we're stuck with the Chinese remainder theorem again, but this one's really easy. It's just 8, because 8 is 8 mod 125 and 0 mod 8. So our final answer is going to be 8. And the last 3 digits are 0, 0, 8. If it was an AIME problem, this one's not an AIME problem, but I can still write it like that. Yeah. But basically, the key idea for this problem is you just apply Totient Theorem a ton of times, along with Chinese remainder theorem to get rid of like all the powers of 2, and then you can like narrow it down. You can just simplify everything. Yeah. basically, when you use Totient Theorem, the key thing is the stuff in the mods gets smaller, and for this problem at least, because the exponents, like, they're basically the same size. But in general, like, the exponents get smaller and the mods get smaller, so it's really nice. So yeah. I guess, yeah, that's it. Also, don't forget to use Chinese remainder theorem. Like, it's really useful because a lot of times k and n won't be relatively prime, and then you can't apply Euler's. But if you make them relatively prime, then you're good. I guess I'll go prove like how you figure out totient. I'm not really sure. Like, I don't know exactly how you do it, but I think basically, like, the idea I have is you can just consider like all the residues, right? So let's say you have n, and it's like p1 to the e1 times p2 to the e2, right? pk to the ek. Then you can consider all the non-zero residues mod each of these, right? So you basically have like p1 minus 1 residues mod p1 that are relatively prime to n, and same thing with like p2, and then so on, right? And this is, I think, where this expression comes from, basically. But you have all of these, but the Chinese remainder theorem says once you have a residue mod like each of the PIs, you can get a residue mod the product of the PIs, which is like P1, P2, ... pk. You can get one residue mod this and exactly one that correspond to all of those residues, right? So you can basically go through, you can just go through all the residues here, and you can multiply them because you choose one from each, right? That's how this works. And then there's basically this many residues mod this thing that work. So it's just n times like the fraction. Yeah. I don't think that's rigorous, but that's basically the idea if you use Chinese remainder theorem. And I think it's pretty clear, like, how you calculate totient. It shouldn't be too hard. A lot of the times it's not very hard. Also, like 125. Yeah. I guess that's it. So if anyone has questions, you guys can work on the exercises and we'll answer questions.